Okay, let's continue. So before we start, I wanted to discuss one problem which I couldn't discuss in detail the last time. So this was the same simple RC circuit that we noticed. So here, if we go by our basic logic, how many poles I should have technically? 2 poles. And how many zeros I can have here? 1 0, because I can short one of the capacitors. But of course, as you know, you can simplify this to a single capacitor. So this results in an effectively a 1 pole system. And we argued that the additional pole and 0 were actually cancelling each other. To prove that point, let me take the same circuit. So I'll take the same network, that is, I'll say V in is 0, but instead I'll change the location of the input and I'll call the current In as the input. And I'll now define this as my output. You can remember, structurally both the networks are identical. By that what I mean is the networks have the same graph, which means if I make the independent excitations to be 0, in both the case the circuit is identical, right? So I have not touched the basic characteristic or graph of the circuit, so expect that the pole location should be same, right? So again the same circuit, so if you make the input to be 0, you have once again 2 poles. And how many zeros will it have here? How many capacitors I can short here? Which one? The top capacitor or bottom capacitor? You can short the top capacitor, so we expect that I should have 1 0. Right? So let's actually, since it's a simple circuit, we can directly calculate the transfer function. So let us say V out of S, that is I in of S, times the impedance we have. And what is the impedance we have here? 1 by SC. Plus, okay, actually I probably, let's say, look at this as the output instead. Yeah, so now what is it? Can you tell me? So I in of S into what will be the current flowing here? So what is the current flowing in this branch? 1 by SC upon right? That okay? So once again, technically, if you try to find here, so you will have 1 by SC times you will have SC. So this will be your actual transfer function, and you will end up with a case where these two guys actually tend to cancel. Okay. Yeah, okay, fine, yeah. Cool. Okay, so let me move on. So today I'll just give a quick recap of what we have done so far and then we'll continue. So just to give a quick recap, we started with the goal of making this fellow, right? And we decided that we need to have amplification. And when I say amplification, what kind of amplification are we referring to? Power amplification, right? And for getting power amplification, what kind of devices do we need? Linear or non-linear? nonlinear, and we saw that we need nonlinear devices because in general we cannot generate any power of our own. Only thing we can do is convert energy from one form to the other. So with a nonlinear network, you power it with a DC source. So you drop DC power and basically convert some of the power to the signal power, and that's how we get large signal power, right? And we started with a single port nonlinear network, and although the network is nonlinear, for small signals, how can you treat the network as linear? And if it's a single port nonlinear network like this, for small signals, how can you model it as a resistor? So if the current is some f of e, what will be the value of the resistor? 1 by the first derivative of at the operating point, right? But then we recognized, one port network doesn't isolate the input and the output, so we went with the 2-port nonlinear network. So again, a 2-port nonlinear network for small signals, how can you model it? It's a 2-port nonlinear network. For small signals, how can you model it? Sorry? Is it just a voltage control voltage source? In general, how can you model this? Sorry? Y parameters. Again, remember, here I had just one voltage and one current. So for small signals, that voltage and current are linearly related. Here, how many voltages and currents I have? So essentially, I have 2 currents, let us say, and 2 voltages. Once again, for small signals, each of these currents will be linearly dependent on each of the 2 voltages. And this is where you get the Y parameters, small signal Y parameters. And the model is this. I mean, if you don't recollect, you have a voltage controlled current source on both sides with a resistor here with the appropriate parameters. But then we noted that if you want to get, if you want to have a good amplifier, of these, which parameter should be non-zero? Y21 should be non-zero, and it should be very small or very large, and Y22 should be, and all these also must be 0. And it turns out transistor is one such device which has this property. So we started look at MOS transistor. So again, you want to make sure that the MOS transistor is biased in a region where you get this small signal characteristics. And what is the region? Saturation region. So then we saw how to bias a transistor in saturation. So we basically looked at a constant voltage or constant current biasing. And what do you prefer, voltage or current? Why? Yeah, in general, if you have any variations in your threshold or something, operating point current, GM, everything changes if you bias it with a constant VGS. A better thing is to bias it with a constant current so that the operating point current doesn't change, the GM doesn't change so much. And how do you bias with a constant current? What is the basic principle you use? Yeah, you use some kind of feedback. So you sense the current. And where all can you sense the current? Either at the source or at the drain. You sense the current, and then what do you do? Yeah, but I mean, you sense the current, just I sense the current, I directly do it, or I should do something else? I should compare the current with a required current you want, and then I basically change which voltage? Gate or source. So you can have multiple combinations, and we saw 2 such commonly used biasing techniques. So which means now after we knew about how to bias the transistors, we looked at small signal behavior. So this was your simple common source. So what is the small signal V out here in terms of Vi? Minus Gm R0 times Vi. Right? And here what this is common source. So what configuration are we putting this transistor in? Common drain. So if you assume that first R0 is infinity here, what can you say about small signal V out? Yeah, why? Yeah, I mean, okay, this is source voltage, yeah, but why is the source voltage equal to the gate voltage? The small signal current here is why? I mean, you should be able to answer why at all possible levels. Only if you are able to answer it, which means you understood it completely, right? Yeah, I mean, okay, here I don't even have current source. I have drawn only the small signal. So what is the impedance here? infinity, open circuit. So what is the small signal current? So if the small signal current is 0, what can you argue? Yeah, GM VGS is 0. So which means, you know, GM is finite, so VGS is 0. So which means the gate and source should be equal. Now if I have finite R0, what happens? Yeah, why? Yeah, correct. But why can't you make the same argument that, you know, here it's still open circuit? Yeah, you have, remember, now you have a path through the R0 for the current to flow. So which means you will have a finite, you know, current still flowing here, and the gain you can find it to be GM R0 by. Again, say need to check, you can tend R0 to infinity. This should tend to 1, that is this case. So now let us say you have something like this. Now instead you have a resistor or a current source which has an output resistance Rs, let us say. So once again, if R0 goes to infinity, what can you say about V out? GM times? I mean, look at these two circuits. So here I had R0 connected from the source to small signal ground. Here I have a resistor connected from source to ground. So what is the expression? GM times Rs by. If I include R0, what happens? Yeah, R0 is going to just come in parallel with R0, so you can just. So this is common drain. So let's look at common gate. So here if I apply a small signal Vi, and if I ignore R0 to start with, let us say R0 is infinity. So what is the V out here? How much? Yeah, what is the small signal current flowing up? Minus GMVI or plus GMVI? Plus GMVI. So V out is? So again here we can check this. So let us say remove this. If I ignore R0, what is the resistance here? If I ignore R0, it is exactly 1 by GM. In presence of R0, what is this expression finally? Yeah, R0 plus RD by 1 plus GM. So which means if let us say RD is really large, so which means let us say RD is open circuit, what is the looking in resistance? Yeah, looking in resistance should be, because once again here open circuit, there is no path for any test current to flow, so it is infinity. It's also apparent from this expression. Okay. So basically, as we know, among these three, which is a better amplifier? Common source. Why not common gate? Common gate also is giving some gain. Looking in impedance where? Yeah, I mean, for a good voltage amplifier, you want to have the input impedance to be how much? You want to make sure the entire voltage is sensed across the amplifier. Here the looking in resistance you see is really small, unless you put an open circuit here, but that is not practical. So that's why we prefer this. And so we started with this and then made a differential amplifier. But then to increase the gain, instead of a resistor, what did we use? Yeah, why can't I keep increasing the value of the resistor here? Yeah, I mean, if I increase the resistance value here, remember the current here is fixed to be I0 by 2. So which means the drop across RD increases, this voltage goes down. So what happens? The transistors go out of saturation. So that's why we use the current source like this. So once again we made a differential amplifier, and then we saw we can actually generate this bias voltage by doing a self bias connection like this. That gave rise to our very popular 5 transistor OTA. So here the main point to have in mind is, although this is asymmetric, when can you claim the circuit to be symmetric? We have common mode excitation, which means the gate to source voltage is same for both of these transistors, NMOS and PMOS, right? So as long as I have the same VGS, which means I have common mode excitation, what can you say about the two drain voltages? Yeah, same. So how can you argue that they are same? you can assume that, you can assume that I say one voltage is greater than the other. Then you will find, let's say, drain voltage for NMOS transistor here is greater, so this current should be greater. Whereas for the PMOS, it will show that this current should be smaller. You will have a contradiction, which means the only logical possibility is for this to be equal. And in general, if I have a differential amplifier with two inputs V1, V2, how do I analyze a circuit? You basically decompose as a common mode part, that is the average, and a differential mode part, that is basically V1 minus V2. The reason is simple. You actually want to see how the amplifier responds to a differential signal, and also if I have a common mode excitation, we know these two voltages are equal, I can basically short them. Circuit also reduces. And one thing to notice, this common mode part is true even for large signals, right? Because here we are only looking, we are only using the fact that if these two voltages are not equal, we'll have a contradiction. So even for large signal, we can say that these two are equal and we can short it. Right? Now similarly, if I have a differential mode signal, if the circuit is truly symmetric, if I have say plus V and minus V here, what can you say now? This node voltage will be 0. Again, this is true only for linear circuits, so which means for small signals you can say. And we also noted that even though we might have asymmetry here, when can you argue that Vx is 0? Yeah, if we ignore the R0 for the NMOS transistors, we can say, because again the reason is the asymmetry is at this node. It is the R0 of the transistors which couple this asymmetry to this node. So if you get rid of them, you are fine. So here, to increase the gain, what did we do? Okay, here the gain you can find as Gm times Rout. Now to increase the gain, what did we do? Did we increase Gm or Rout? So what was the first thing we did? We put a cascode. So this is your normal cascode. So what is the output resistance here? If I call this M1, M2, Gm of which transistor? R0 1 times. Roughly this is the thing, and using this we basically made a cascode like this. Again, we have to do self biasing here. We could do this, or we also saw we can do this, but as we discussed, doing this results in a better output swings. So this is done generally. And after, but this is the telescopic cascode. What was one drawback with telescopic cascode? Do you remember? Yeah, if I use it in unity feedback, what happens? Yeah, there is no room for the voltage to swing if you design for max output swings. That is, if you design this telescopic op amp to have the maximum output swings, then if you put in unity feedback, there is no room. So which means you cannot design for maximum output swings. But even if you do this, the overall swing you have will be really small. And what was a fix we did for that? We need to folded cascode. What is folded cascode? Yeah, exactly. So if I have current source as NMOS, current buffer will be PMOS. So you'll have something like this. So similar, or if the current source is a PMOS, current buffer should be, so which means I have an NMOS current buffer, so the current will be going here. Right? This is your output. So that gave rise to folded cascode, and then to increase the gain of the folded cascode further, what did we, increase the gain of the cascode further, what did we see? We looked at GM boosting. Again, the idea is the following. If I take a normal cascode, I can take a normal cascode. The observation is the following: if the drain voltage of this current source doesn't change, the output resistance is also infinity, and which means I can go and put a large gain in negative feedback. If the gain A is really large, as this gain A tends to infinity, what can you say about this voltage? That has to go to 0. So that's why we get a large gain. And again, then we looked at the poles and zeros, etc., etc. Finally, we concluded that all the OTAs that we have seen are single stage OTAs. And how can you model it as a first order or a second order system? So typical model for the OTAs is you assume that you have a short circuit GM and intrinsic R out, and the dominant pole is assumed to be at the output due to the load capacitor. So this is your single stage OTA. But what is the limitation with single stage OTA? Sorry? Yeah, what is the, I mean, you can't drive small resistive loads. Why? Yeah, if you put a small resistive load here, the output resistance significantly drops. So that gave rise to the motivation for multi-stage OTA. And we looked at a simple two-stage OTA like this. So here the important point we noted was, if I use it in open loop and provide DC voltage at the inputs, is the output voltage defined? Not defined properly, because remember I have two current sources biased independently. If for example one of the currents is, say I5 is much greater than I2 to start with, what will happen to Vout? This current is greater than this current, Vout will drop. So if it goes beyond a point, M5 goes out of saturation or vice versa. Right? So the point to notice, I mean, one thing I want to clarify is, it is not that, you know, all the time this transistor can go out of saturation. Maybe there is, you know, if all the stars and planets align, maybe the voltage here drops, but still the transistor remains in saturation to keep the two currents equal. But that's not a great thing, because once again threshold voltage can change with temperature. If threshold voltage changes, this will easily go out of saturation. So this is not the best way to bias it. So what should you do? Should have some kind of negative feedback around the op amp, and this is what we do. If I do this, I still have two current sources, but are the two current sources biased independently? Are both the current sources independently biased? Which of the current sources independently biased? M6 and M5. You see, the gate voltage is not independently available to you. It is basically set by the negative feedback system. So this way we kind of avoid it. And the last class, few classes back, we also saw how do you determine if you are in negative or positive feedback. Sorry. Yeah. So this is your classic negative feedback. How do you check this is input? Let us say. Yeah. This is input output. So before breaking the loop, what do you do to the inputs? You can make the inputs to 0, and then you kind of break the loop anywhere. So this is a, you know, idealistic model. I can break the loop any point, and then I try to increase the voltage. And remember, the whole point of having negative feedback is to make sure that you have an accurately defined output quantity, right? So which means if there is any change, first of all, let me mark it this way, right? So what is the closed loop gain here from input to the output? A by, for very large values of A, what is this approximately? So that's the whole point of negative feedback, that in open loop this gain A can change a lot, but as long as this is sufficiently large, the closed loop gain remains constant roughly. That's the whole point of having negative feedback. That is, if the voltage in the loop changes for some reason, the loop should act in such a way to suppress that change, right? So which means if I to check if I'm in negative or positive feedback, I make some change and then see what comes back. So here you'll find that the output kind of reduces. So that's the principle of negative feedback, that any change that is made within the loop will act in such a way to suppress that effect. Cool. So let's continue. But before that, this whole idea of, a system trying to suppress any change it sees, have you encountered it? When did you first encounter this? When did you? I mean, okay, I mean, when you learned, right, in your curriculum, when was the first time you encountered this negative feedback? Control systems. You guys are lying, man. You learned in physics, high school physics. Can you think, I mean, in physics, did you learn something wherein if you make some change, the system will act to suppress it, some physics laws that you learned? Huh? Inertia, correct. Lenz's law, all law and everything, right? Everything. I mean, basically that's all negative feedback system, right? Lenz's law is same, right? You make some change, the system will basically act to counter and suppress the change. So fundamentally everything is negative feedback. Right? Just that this term negative feedback was not thrown at you.